Modern computing systems can write complex application code in seconds and diagnose obscure medical illnesses with high accuracy. Yet, despite these capabilities, they possess exactly zero comprehension of the physical world they operate in. We use the term artificial intelligence to describe these tools. In practice, that phrase refers to a broad collection of statistical models and predictive math. The popular image of a conscious, feeling machine making independent decisions does not exist in any server rack today. Instead, the reality of AI is a 70-year engineering struggle. It is the story of humans trying to map our own logic into hardware, and the surprising method that finally made it work. That effort formally began at Dartmouth College in 1956. Researchers gathered at a summer workshop, and computer scientist John McCarthy coined the term artificial intelligence. For decades, the dominant approach was known as symbolic AI. The theory was straightforward. Human thought could be perfectly simulated if engineers simply fed computers the right rigid rules and mathematical logic. But researchers quickly encountered a fatal flaw. Mathematical proofs and chess moves were easy to program. Human perception, natural language, and common sense proved impossible to hardcode. There were simply too many variables in daily life for a programmer to anticipate. These brittle, expert systems failed to meet the lofty expectations set by their creators. By the 1970s and 80s, government agencies and corporations cut their funding in response, leading to periods of deep stagnation known as AI winters. Trying to build intelligence through strict rules had hit a definitive wall. Building intelligence through strict rules hit a definitive wall. To make machines more capable, humans had to stop telling them exactly how to think. The solution emerged when vast amounts of data became available through the internet, paired with a massive increase in processing power. Researchers pivoted to machine learning, a method that allows systems to analyze data and identify statistical patterns on their own, without explicit programming. This approach yielded highly capable, specialized tools, known as narrow AI. In 1997, a machine successfully recognized board patterns well enough to defeat human world champion Garry Kasparov. The IBM Deep Blue supercomputer required an enormous, custom-built hardware stack to win that match. The chess victory demonstrated that pattern recognition could effectively mimic human expertise. It set the stage for modern systems that rely entirely on statistical probability rather than genuine knowledge. This animation illustrates the core mechanism of modern generative AI. When you ask a chatbot a question, it does not consult a factual database. It builds a response step by step by predicting the next most probable word based on the immense datasets it was trained on. These probabilities are calculated inside neural networks, which use interconnected layers of nodes to loosely mimic the structure of a biological brain. This architecture allows the system to process massive amounts of unstructured, unlabeled data. The system achieves its conversational fluency through an architecture called transformers. Instead of reading a sentence one word at a time, a transformer processes entire sequences of data simultaneously, allowing it to maintain context over long paragraphs. But because the system is constantly guessing the next word based on probability, it is highly prone to what researchers call hallucinations, generating confident, detailed statements that are entirely false or nonsensical. Hallucinations are not a software glitch. They are an inherent feature of the technology. The system is mathematically designed to calculate patterns that sound plausible, not to verify objective truth. The trade-off of generative AI is clear. We have achieved incredible conversational capability and speed, but we have completely sacrificed guaranteed factual accuracy in the process. In the early 2020s, these pre-trained foundation models broke out of the research lab and became a massive worldwide consumer utility, integrated into search engines, productivity software, and mobile devices. When applied in the right contexts, these tools provide immense efficiency boosts. They can rapidly analyze vast arrays of medical diagnostics or ingest real-time data to optimize global supply chains. Yet their performance remains entirely tethered to their training data. If the input data lacks diversity or contains historical prejudices, the probabilistic model will inevitably replicate and amplify those exact blind spots in its output. An AI model is never neutral. It is a highly capable, high-speed reflection of the specific information its human creators chose to feed it. While we interact with AI as invisible software in the cloud, it demands massive physical infrastructure. These systems require immense data centers, filled with thousands of specialized processors. It takes massive energy spikes simply to train a large language model initially. But there is also an ongoing energy cost, known as inference, which is incurred every single time a user enters a prompt or requests an image. Beyond the environmental footprint, unleashing probabilistic generation on the public has triggered immediate socioeconomic fallout. This ranges from the rampant creation of deceptive deepfakes to the mass copyright infringement of the original artists and writers whose work comprises the training data. The cost of artificial intelligence is paid in real-world resources and societal trust. Raw computational capability cannot exist safely in the public sphere without rigorous external safeguards. This diagram outlines the NIST AI Risk Management Framework. It represents a critical attempt by policymakers to establish standard protocols for evaluating and containing predictive systems across industries. A vital part of this containment is red teaming. Before a model is released, human experts intentionally try to break, manipulate, or bypass its safety filters to expose vulnerabilities. Right now, the landscape relies heavily on voluntary corporate safety guidelines. But as models grow more complex, there is a mounting international push to replace those promises with binding government regulations. These frameworks exist because the machine itself possesses no agency, no morality, and no comprehension of its own impact on the physical world. The greatest challenge of this era is not preventing a computer program from becoming human. It is ensuring that humans take unyielding responsibility for the systems they choose to build.